By the late 19th century, physics stood at what many believed was its moment of completion. The laws governing motion, energy, heat, light, and matter had been refined over centuries, forming a grand structure that appeared solid and unshakable. Isaac Newton's mechanics explained the movement of planets and falling objects with astonishing accuracy. James Clerk Maxwell's equations unified electricity, magnetism, and light into a single elegant framework. Thermodynamics described heat and energy with mathematical precision. To most physicists of the time, the universe seemed fully mapped, its mysteries reduced to calculation. This confidence was so strong that some prominent scientists openly suggested there was little left to discover. The future of physics, they believed, lay not in uncovering new principles, but in improving measurements and refining decimal places. Nature appeared continuous, deterministic, and predictable. If the position and motion of every particle were known, the future could, in theory, be calculated exactly. This world, you reflected not only scientific belief, but also the broader intellectual spirit of the age, one that trusted reason, order, and certainty. Yet beneath this apparent success, cracks were forming. These cracks did not appear dramatically or suddenly. Instead, they emerged quietly in laboratories, in experimental results that refused to align with established theory. At first, these inconsistencies were treated as minor inconveniences rather than fundamental threats. Scientists assumed that small corrections or improved techniques would eventually resolve them, but the problems persisted, growing more troubling with each failed attempt at explanation. One of the most serious challenges came from the study of heat and radiation. Physicists sought to understand how objects emit light when heated, a phenomenon observed in everything from glowing metal to the light of stars. According to classical theory, energy should be emitted smoothly and continuously across all wavelengths. Mathematical models predicted how much radiation an object should emit at different frequencies as its temperature increased. Initially, these models worked reasonably well at low frequencies, reinforcing confidence in classical physics. However, when these same equations were applied to higher frequencies, particularly in the ultraviolet range, the predictions became absurd. The mathematics suggested that a heated object should emit infinite energy at short wavelengths. This result was not just inaccurate, it was physically impossible. Experiments showed that radiation intensity rose to a peak and then dropped sharply, not exploded into infinity. This contradiction became known as the ultraviolet catastrophe, a name that reflected both its severity and the threat it posed to classical theory. The ultraviolet catastrophe was more than a technical problem. It struck at the heart of the classical world view. If the most trusted equations of physics led to nonsensical results, then something was fundamentally wrong. Scientists tried various fixes, adjusting assumptions and modifying formulas, but none could fully resolve the issue without introducing new inconsistencies elsewhere. The crisis deepened as it became clear that this was not an isolated anomaly, but a symptom of a larger failure. At the same time, other troubling observations began to surface. The behavior of atoms, long assumed to be miniature versions of larger mechanical systems, defied explanation. Classical physics predicted that electrons orbiting a nucleus should continuously lose energy and spiral inward, causing atoms to collapse. Yet atoms were stable, matter existed. The everyday world contradicted theoretical expectation. Once again, the mathematics of classical physics clashed with physical reality. Light itself became another source of confusion. Maxwell's equations described light as a wave, and wave theory explained many optical phenomena beautifully. Interference, diffraction, and polarization all confirmed the wave nature of light. But certain experiments, such as the photoelectric effect, revealed behavior that waves could not explain. Light appeared to act as if it were made of particles, transferring energy in discrete amounts rather than spreading it smoothly across space. Each of these problems alone was troubling. Together, they formed a growing sense of unease. Classical physics, once seen as a complete and perfect description of nature, now appeared limited and fragile. The crisis was not merely about missing details. It was about the foundations of understanding. The assumption that nature was continuous, deterministic, and infinitely divisible no longer held up under experimental scrutiny. What made this crisis particularly difficult was that there was no obvious alternative. Classical physics had been built gradually through centuries of success. It was deeply embedded in scientific thinking, education, and culture. Abandoning its principles felt almost unthinkable. Many physicists hoped the problems would eventually disappear, resolved by clever mathematics or improved experimental methods. Few were willing to consider that the entire framework might need revision. This resistance was not due to arrogance, but to the extraordinary success classical physics had achieved. It had explained the motion of planets, predicted new celestial bodies, powered the Industrial Revolution, and transformed technology. To suggest that such a powerful system was incomplete felt almost disrespectful to its legacy. Yet nature does not conform to human pride, and the experimental evidence continued to demand answers. The crisis in classical physics was also philosophical. It challenged deeply held beliefs about causality and certainty. Classical mechanics assumed that every effect had a precise cause, and that randomness reflected only ignorance, not fundamental uncertainty. If physics could no longer predict outcomes with absolute certainty, what did that say about reality itself? Was the universe inherently unpredictable at its core, or were scientists simply missing hidden variables? These questions unsettled not only physicists, but philosophers as well. The idea that nature might operate according to probabilities rather than certainties threatened the Enlightenment ideal of a fully rational and knowable universe. Science had long been seen as a path to objective truth, free from ambiguity. The emerging crisis suggested that ambiguity might be unavoidable. As the 19th century drew to a close, the tension between theory and experiment reached a breaking point. The old equations still worked brilliantly in many situations, but their failures could no longer be ignored. Physics stood at a crossroads, though few realized how dramatic the coming transformation would be. The crisis was silent, unfolding in equations and experiments rather than public debates, but its implications were revolutionary. It was within this atmosphere of uncertainty that Max Planck entered the scene. He was not a radical thinker or a rebellious scientist. He believed deeply in the orderliness of nature and the validity of classical laws. Yet he was confronted with experimental data that refused to cooperate. Like many before him, he tried to solve the radiation problem without abandoning classical principles. What he found instead would quietly mark the beginning of a new era. The crisis of classical physics was not a sudden collapse, but a gradual realization that the old map of reality was incomplete. It revealed the limits of human intuition shaped by everyday experience. The world of atoms and energy did not behave like the world of machines and planets. Something fundamentally different was at work, waiting to be understood. This moment in history reminds us that scientific progress does not always come from bold declarations or dramatic revolutions. Sometimes it begins with discomfort, with the recognition that trusted ideas no longer explain observed facts. The crisis of classical physics was such a moment, a quiet but profound turning point that forced science to confront its own assumptions. By exposing the gaps in classical theory, this crisis prepared the ground for a new understanding of reality. It created the conditions in which radical ideas could emerge, even from cautious minds. The failure of classical physics was not the end of science, but the beginning of a deeper and more accurate description of the universe. And it was this silent tension between certainty and contradiction that set the stage for the quantum revolution that would soon follow. To ignore, the scientific community found itself in a state of uneasy persistence. Equations that had once felt unbreakable were now surrounded by exceptions. Physicists continued to teach and apply classical laws because they still worked remarkably well at everyday scales. Yet there was a growing awareness that these laws were not universal. They were approximations, accurate only within certain limits. This realization alone marked a profound shift in how science viewed its own authority. Laboratories across Europe became the front lines of this crisis. Precision instruments revealed behaviors that defied established theory with increasing clarity. These were not errors of measurement or flaws in technique. The experiments were repeatable, consistent, and undeniable. Each confirmation strengthened the conclusion that the problem lay not in observation, but in theory itself. Classical physics, for all its elegance, was incomplete. One of the most unsettling aspects of this crisis was its impact on the concept of energy. In classical thinking, energy was continuous, infinitely divisible, and smoothly transferable. This idea fit perfectly with mechanical intuition. A swinging pendulum could lose energy gradually, and heat could flow seamlessly from one object to another. Yet atomics, Gale phenomena did not obey this smoothness. Energy exchanges appeared abrupt, selective, and constrained in ways that classical models could not justify. The stability of matter posed an especially troubling question. According to classical electrodynamics, charged particles in motion should continuously emit radiation and lose energy. If atoms followed these rules, electrons orbiting a nucleus would rapidly spiral inward, collapsing the atom in a fraction of a second. The fact that matter existed at all was a direct contradiction of classical predictions. This was not a minor oversight, but a complete failure to describe the basic structure of reality. Physicists attempted to rescue classical theory through increasingly complex assumptions. Some proposed that unknown forces or mechanisms prevented atomic collapse. Others suggested that classical laws might somehow break down at small scales without requiring a full conceptual overhaul. These explanations, however, lacked experimental support and often created more problems than they solved. The deeper scientists looked, the clearer it became that classical physics could not simply be patched. The crisis also exposed the limits of human intuition. Classical physics had been shaped by everyday experience, by objects large enough to see and touch. At the atomic level, however, nature operated in ways that defied common sense. Concepts like trajectory, position, and velocity, so natural in the macroscopic world, became ambiguous and unreliable. This disconnect forced physicists to question whether intuition was a reliable guide to fundamental truth. Resistance to change was strong, and understandably so. Accepting that classical physics was incomplete meant accepting uncertainty at the heart of science. It meant admitting that centuries of confident assumptions had boundaries. Many scientists found this deeply uncomfortable. They had built their careers and identities on the belief that the universe was ultimately predictable and orderly. Letting go of that belief felt like stepping into chaos. Yet the crisis also created an opening. Younger physicists, less attached to classical traditions, were more willing to explore unconventional ideas. They were motivated not by rebellion, but by necessity. The data demanded explanation, and existing theories could not provide it. This tension between tradition and innovation became a driving force behind the transformation of physics. The role of mathematics during this period became increasingly complex. Classical equations had once provided clear, deterministic answers. Now they produced infinities, contradictions, and undefined results. Mathematicians and physicists alike struggled to interpret these outcomes. Were the equations wrong, or was their interpretation incomplete? This uncertainty blurred the boundary between mathematical formalism and physical reality. The crisis also highlighted the importance of humility in science. The belief that physics was nearly complete proved to be an illusion. Nature revealed itself to be far richer and stranger than previously imagined. This realization served as a reminder that scientific knowledge is provisional, always subject to revision in the face of new evidence. Progress did not mean final answers, but deeper questions. As experimental evidence accumulated, the idea that classical physics was universally valid became impossible to defend. Instead, it became clear that classical laws were special cases, accurate under specific conditions, but not fundamental. This shift in perspective was subtle but revolutionary. It transformed classical physics from a description of ultimate reality into an approximation of a deeper framework yet to be discovered. The crisis also reshaped the goals of physics. Rather than seeking a single, all-encompassing description of nature based on everyday intuition, scientists began to accept that reality might operate according to multiple layers of laws. Different rules could apply at different scales, and no single set of concepts might fully capture the behavior of the universe. This idea would have been unthinkable in earlier generations. Emotionally, the period was marked by both frustration and excitement. Frustration came from repeated failures and unresolved contradictions. Excitement came from the sense that something extraordinary lay just beyond reach. The breakdown of classical physics did not signal defeat but transformation. It suggested that a deeper truth was waiting to be uncovered, one that would challenge existing beliefs and expand human understanding. The crisis also altered the relationship between theory and experiment. In classical physics, theory often guided experiment, predicting phenomena before they were observed. During this period, experiment took the lead, forcing theory to adapt. This reversal underscored the empirical foundation of science. No matter how elegant a theory might be, it must ultimately answer to nature. By the time Max Planck proposed his radical assumption about energy, the ground had already been prepared. The crisis of classical physics had created a space in which new ideas could be considered, even if reluctantly. Without this widespread sense of failure, Planck's proposal might have been dismissed outright. Instead, it was recognized as a possible way forward, however unsettling it seemed. In hindsight, the crisis of classical physics appears inevitable. The universe was never obligated to conform to human expectations. The success of classical theory had been real, but limited. Its breakdown revealed not a flaw in science, but its strength. Science advanced because it was willing to confront its own failures and learn from them. This period stands as one of the most important transitions in the history of knowledge. It marked the end of the illusion of completeness and the beginning of modern physics. The crisis forced scientists to abandon absolute certainty and embrace a more nuanced understanding of reality. It taught that progress often begins not with answers, but with the recognition that old answers are no longer enough. The silent crisis of classical physics did not unfold in a single moment, but over decades of careful observation and growing doubt. Its impact, however, was profound and lasting. It reshaped how humanity understands nature, knowledge, and the limits of reason. From this quiet breakdown emerged a new vision of the universe, one that would redefine reality itself. And in that sense, the crisis was not a failure, but a necessary passage. It was the moment when physics outgrew its own foundations and prepared to step into a deeper, stranger, and more truthful understanding of the world. In the quiet laboratories of the 19th century, one of the most ordinary physical phenomena slowly revealed itself to be one of the most dangerous challenges classical physics had ever faced. It was not a distant star, a rare particle, or an exotic substance that caused the trouble, but heat itself. When objects are heated, they glow. This simple observation, familiar from hot iron to the warm light of a stove, became the gateway to a crisis that would expose the limitations of old theories and force science to rethink the nature of reality. Physicists sought to understand how heated objects emit radiation. To study this process in its purest form, they introduced an idealized concept known as a blackbody. A blackbody was imagined as a perfect absorber of radiation, one that absorbed all incoming light and re-emitted energy based only on its temperature. This concept allowed scientists to strip away complications and focus on fundamental laws. It seemed like a straightforward problem, perfectly suited to classical physics. At first, classical theory appeared capable of handling the task. Using established principles of thermodynamics and electromagnetism, physicists developed mathematical models to describe the spectrum of radiation emitted by a blackbody. These models predicted how much energy would be radiated at each wavelength for a given temperature. Early experimental results matched the predictions reasonably well at longer wavelengths, reinforcing confidence in the existing framework. But as measurement techniques improved, the picture began to change. Experiments revealed that radiation intensity did not increase endlessly with frequency. Instead, it rose gradually, reached a peak, and then declined sharply at higher frequencies. This behavior was consistent across all temperatures and materials. Classical equations, however, stubbornly refused to follow this pattern. According to classical physics, energy within a cavity could oscillate at any frequency and absorb any amount of energy. This assumption led directly to a catastrophic conclusion. The equations predicted that as frequency increased, the amount of emitted energy would grow without limit. In theory, a blackbody should radiate infinite energy in the ultraviolet range. This prediction was not just incorrect. It violated the most basic principles of conservation and common sense. The absurdity of this result could not be ignored. If classical theory were correct, every warm object would emit an unlimited amount of high-frequency radiation, instantly releasing infinite energy. Clearly, this did not happen. The contradiction was so severe that it earned a dramatic name, the ultraviolet catastrophe. Behind the dramatic label lay a profound truth. Classical physics was failing at a fundamental level. What made the situation especially troubling was that the mathematics itself was flawless. The equations were derived logically from well-established principles. There were no calculation errors, no missing terms. The problem was not with the math, but with the assumptions underlying it. This realization was deeply unsettling. If the assumptions of classical physics led to impossible conclusions, then the foundations themselves were unstable. Scientists attempted to fix the problem without abandoning classical ideas. Various models were proposed to modify the energy distribution at high frequencies. Some approaches worked temporarily within limited ranges, but none provided a universal solution. Each fix seemed artificial, lacking a clear physical justification. The more adjustments were made, the more strained the theory became. Blackbody radiation became a mirror reflecting the limits of classical thinking. It revealed that nature did not distribute energy smoothly and continuously, as physicists had assumed. Instead, something more subtle was happening at microscopic scales, yet no one knew what that something was. The data demanded explanation, but the language of classical physics was no longer sufficient. The crisis was intensified by the fact that blackbody radiation was not an obscure phenomenon. It was everywhere. Stars approximate blackbodies. Heated metals glow. Even the background radiation of the universe follows blackbody behavior. This meant the failure of theory was not confined to rare conditions, but applied to the most common processes in nature. The flaw was universal. Emotionally, the situation created tension within the scientific community. Blackbody radiation was a problem that refused to disappear. Each new experiment confirmed the same spectral curve, mocking classical predictions. Physicists were forced to confront a disturbing possibility: that their understanding of energy itself was incomplete. The failure to explain blackbody radiation also challenged the philosophical commitment to continuity. Classical physics was built on the idea that physical quantities could vary smoothly and infinitely. Temperature, energy, and frequency were treated as continuous variables. Blackbody radiation suggested that this assumption might be wrong. The universe seemed to impose limits where none were expected. This realization was particularly difficult because it contradicted centuries of intuition. Continuous change felt natural and obvious. Discrete behavior felt artificial, imposed rather than discovered. Yet the experimental evidence was undeniable. Nature was refusing to behave according to human expectations. The problem of blackbody radiation also exposed a deeper issue in the relationship between matter and radiation. Classical physics treated electromagnetic waves as independent of the atomic structure of matter. Radiation was described as a field, spreading continuously through space. Blackbody experiments, however, hinted that radiation was intimately connected to the microscopic properties of matter. Something at the atomic level was controlling how energy was emitted and absorbed. As the 19th century drew to a close, the blackbody problem became impossible to ignore. It stood as a clear signal that classical physics had reached the limits of its explanatory power. The flaw was not minor or technical. It was fundamental. It touched the core assumptions about energy, matter, and the nature of physical law. This moment marked a turning point. The inability to explain blackbody radiation forced physicists to consider ideas that once seemed unthinkable. It created a space for radical solutions, even from conservative thinkers. Without this problem, the transition to modern physics might have been delayed by decades. Blackbody radiation did more than reveal a flaw in old theories. It exposed the danger of assuming that successful models are complete. It showed that even the most elegant and well-tested theories can fail when pushed beyond their limits. In doing so, it reminded science of its most important lesson: nature, not theory, has the final word. The glow of heated objects, once taken for granted, became the signal of an approaching revolution. What appeared as a simple curve on a graph carried within it the collapse of classical certainty. The flaw revealed by Blackbody radiation was not merely technical. It was conceptual, philosophical, and unavoidable. As physicists struggled with this problem, they unknowingly stood on the edge of a new era. The old theories were still powerful, still useful, but no longer sufficient. Blackbody radiation had exposed their limits with quiet persistence. The question was no longer whether classical physics was flawed, but how deep that flaw truly ran. The answer would come soon, not with noise or defiance, but with a simple, reluctant idea that would forever change how humanity understands energy and reality itself. As the Blackbody problem persisted, it began to reshape the daily work and mindset of physicists. What once seemed like a well-defined calculation turned into a persistent reminder that nature was not obligated to follow established rules. Each new measurement of radiation intensity confirmed the same unmistakable pattern, and each confirmation deepened the sense that classical physics was speaking the wrong language when describing thermal radiation. The failure was especially striking because Blackbody radiation involved equilibrium, a state classical physics was supposed to handle perfectly. Thermodynamics had been built precisely to describe systems in balance, where energy flows were stable and predictable. A Blackbody cavity, sealed and maintained at a constant temperature, should have been a textbook example of classical success. Instead, it became evidence of classical failure. This contradiction forced scientists to reconsider how energy was stored and exchanged inside matter. Classical theory imagined countless oscillators within a cavity, each capable of vibrating at any frequency and carrying any amount of energy. These oscillators were treated as independent and unlimited, free to absorb and release energy continuously. It was this assumption, so natural and unquestioned, that ultimately led to the ultraviolet catastrophe. The realization that an assumption so basic could be wrong was deeply unsettling. It suggested that the problem was not with specific equations, but with the conceptual picture of nature itself. Energy, long thought of as a smooth fluid, might have a structure that classical physics could not see. This idea hovered on the edge of acceptability, resisted not because of lack of evidence, but because of its philosophical implications. The Blackbody crisis also blurred the boundary between theoretical and experimental physics. Experimentalists could describe the radiation curve with precision, but they could not explain why it had that shape. Theorists, meanwhile, could produce elegant mathematics that failed spectacularly at high frequencies. The two sides were no longer aligned, and their disconnect highlighted the growing gap between theory and reality. As discussions intensified, some physicists began to accept that continuity might not be a universal principle. The idea that energy could be constrained, limited, or regulated at microscopic scales slowly entered scientific conversation. This was not yet quantization, but it was a shift in attitude. The certainty that energy could vary without restriction was fading. The Blackbody problem also revealed the limitations of reductionism as it was then understood. Classical physics assumed that understanding the parts would automatically explain the whole. Yet even when the behavior of waves and oscillators was well described individually, their collective behavior inside a cavity produced impossible results. This suggested that new principles might emerge at certain scales, principles that could not be reduced to classical components. Beyond physics, the implications were cultural and philosophical. The 19th century had been marked by faith in progress, order, and rational explanation. The idea that a simple heated object could expose a fundamental gap in human knowledge was humbling. It reminded scientists that mastery over nature was always provisional, dependent on models that could be overturned by observation. The persistence of the Blackbody problem also revealed the importance of intellectual courage. Many physicists recognized the flaw but hesitated to pursue radical solutions. The cost of being wrong was high, and the risk of abandoning trusted principles was daunting. Yet the problem refused compromise. It demanded either resolution or surrender. In this environment, the role of Max Planck became pivotal, not because he sought revolution, but because he sought honesty. Faced with experimental curves that could not be denied, he was willing to make an assumption that classical physics forbade. His solution did not emerge from philosophical speculation, but from mathematical desperation. He adjusted the rules not because he wanted to, but because he had to. What followed demonstrated the true depth of the flaw exposed by Blackbody radiation. A single change in how energy was treated resolved the catastrophe completely. The radiation curve fell into place, matching experiment perfectly across all frequencies. This success made one thing clear. The old theories had failed not due to complexity, but due to a mistaken view of energy itself. The quiet success of this new approach forced the scientific community to confront an uncomfortable truth. If a theory based on discrete energy exchanges worked where classical continuity failed, then continuity could no longer be considered fundamental. It might be an approximation, valid only under certain conditions. This realization redefined what it meant for a theory to be true in physics. Blackbody radiation thus became more than a technical problem. It became the first clear signal that the microscopic world obeyed different rules than the macroscopic one. The glow of heated objects revealed that nature imposed limits invisible to everyday experience. These limits were not imposed by measurement or ignorance, but by reality itself. The flaw exposed by Blackbody radiation also altered how physicists approached future problems. It taught them to question assumptions that felt obvious. It demonstrated that success in one domain did not guarantee universality. Most importantly, it showed that contradictions were not obstacles to progress, but invitations to deeper understanding. In retrospect, the Blackbody problem stands as a turning point precisely because it was unavoidable. It could not be ignored, simplified away, or dismissed as experimental error. It involved fundamental concepts and everyday phenomena, forcing physics to confront its own foundations. The flaw it revealed was not hidden or abstract. It was visible in every glowing object, every heated surface, every star in the sky. This crisis transformed scientific humility into a strength. By accepting that classical theories had limits, physicists opened the door to a richer and more accurate description of nature. The failure of old ideas did not diminish their value, it clarified their scope. Classical physics remained powerful, but no longer absolute. Blackbody radiation also demonstrated the quiet nature of true revolutions. There were no dramatic confrontations, no sudden overthrow of authority. Instead, there was a gradual recognition that something simple had been misunderstood. A curve on a graph, repeated again and again, carried more weight than centuries of assumption. The flaw exposed by Blackbody radiation reshaped the future of physics. It set the stage for quantum theory, altered the meaning of energy, and redefined the relationship between theory and experiment. It showed that reality could not be forced into familiar categories, and that understanding often begins where certainty ends. In the end, Blackbody radiation taught science one of its most enduring lessons. The universe does not reveal its secrets to confidence alone. It responds to patience, observation, and the willingness to abandon even the most trusted ideas when they no longer reflect the truth. Through this quiet and persistent problem, classical physics was compelled to step aside, making room for a deeper understanding of reality. The idea that energy exists in fixed packets emerged not as a bold declaration, but as a reluctant conclusion drawn from failure. For centuries, energy had been treated as something smooth and continuous, capable of being divided endlessly without limit. This assumption fit perfectly with everyday experience. Heat could be added gradually, light could grow brighter bit by bit, and motion could change smoothly over time. Classical physics depended on this continuity, and no one seriously questioned it. The crisis came when experiments refused to cooperate with this assumption. Blackbody radiation, atomic stability, and later the behavior of light itself all pointed toward a deeper structure beneath observable smoothness. When Max Planck introduced the idea that energy could only be exchanged in discrete amounts, he was not trying to redefine reality. He was trying to save physics from contradiction. His proposal suggested that energy is emitted and absorbed in small, indivisible units rather than flowing freely. This was a radical departure from classical thinking. According to Planck's idea, energy could not take just any value. It came in specific chunks, each proportional to the frequency of radiation. These chunks were not artifacts of measurement or mathematical convenience. They were required by nature itself. Without them, theory collapsed into absurd predictions. With them, experimental data suddenly made sense. What made this discovery unsettling was its implication that continuity was an illusion. At large scales, energy appears smooth because the packets are extremely small. Their individual effects blend together, creating the appearance of continuity. But at microscopic scales, this smoothness breaks down. Energy reveals itself as granular, constrained by fixed steps that cannot be bypassed. This idea challenged intuition at its core. It suggested that nature operates more like a staircase than a ramp. Transitions occur in jumps, not slides. Objects cannot possess arbitrary amounts of energy, only specific allowed values. This behavior was completely foreign to classical mechanics and deeply uncomfortable to accept. At first, even Planck himself resisted the physical meaning of his discovery. He viewed energy packets as a mathematical trick rather than a statement about reality. Yet the success of the idea could not be ignored. When Albert Einstein applied the same concept to light, explaining the photoelectric effect, it became clear that energy packets were not limited to radiation inside cavities. They were a fundamental feature of nature. The discovery of fixed energy packets reshaped the understanding of matter and light. Atoms no longer absorbed energy continuously. They transitioned between distinct energy states, emitting or absorbing precise amounts in the process. This explained why atoms produce sharp spectral lines instead of continuous spectra. It also explained why matter is stable, why electrons do not spiral into nuclei, and why physical systems exhibit order at the smallest scales. Beyond physics, the idea transformed philosophy. Determinism weakened, certainty faded, and probability entered the description of reality. If energy changes occur in discrete steps, then outcomes cannot always be predicted with absolute precision. The universe, once imagined as a perfectly smooth machine, revealed a textured, structured foundation. The discovery also redefined what it meant for a theory to be fundamental. Classical physics was not wrong, but incomplete. It worked where energy packets were too small to notice, but failed where their discreteness mattered. This layered understanding of reality became a defining feature of modern science. Today, the idea of energy packets is embedded in nearly every advanced technology. Lasers, semiconductors, solar cells, and quantum devices all depend on controlled energy transitions. What began as a desperate solution to a theoretical problem became one of the most powerful concepts ever introduced. The realization that energy exists in fixed packets did not arrive with spectacle. It arrived quietly, through equations that refused to lie. Yet its impact was profound. It revealed that beneath the smooth surface of the world lies a reality built on limits, steps, and structure, waiting to be understood not by intuition, but by evidence. The introduction of Planck's constant marked a moment when nature revealed a boundary that could not be crossed. Before this idea emerged, physics assumed that measurements could, in principle, be made with unlimited precision, and that energy could be divided endlessly into smaller and smaller portions. There was no fundamental scale, no smallest unit that defined the limits of physical description. Planck's constant changed that assumption forever. When Max Planck introduced this constant, it was not intended to redefine reality. It appeared as a proportionality factor in an equation designed to match experimental results. Yet hidden within this small number was a profound message. Planck's constant established a minimum scale for action in the universe, a smallest meaningful quantity that governs how energy and time relate to one another. It was a signal that nature is not infinitely divisible. This constant placed a limit on how precisely certain physical properties could be known or controlled. Energy exchanges could no longer be arbitrarily small. They occurred in steps set by this constant and the frequency of the system involved. At everyday scales, the value of Planck's constant is so tiny that its effects are invisible, allowing classical physics to work extremely well. But at atomic and subatomic scales, its influence becomes dominant and unavoidable. The presence of a fundamental constant reshaped the concept of measurement. Classical physics assumed that with better instruments, uncertainty could always be reduced. Planck's constant implied that uncertainty is not merely a technological limitation, but a feature of reality itself. This idea would later become central to quantum mechanics, where limits on precision are woven directly into the structure of physical law. Planck's constant also changed how energy, momentum, and wavelength were understood. It linked wave, like, and particle, like descriptions of nature, into a single framework. Light, once described purely as a wave, now carried energy in amounts defined by this constant. Matter, once treated as solid and continuous, began to show wave-like properties constrained by the same limit. The boundary between waves and particles started to dissolve. Philosophically, the constant introduced humility into science. It suggested that human knowledge has natural limits, not because of ignorance or lack of skill, but because the universe itself enforces boundaries. This was a radical departure from the classical belief that complete knowledge was theoretically possible. The universe was no longer an open book waiting to be read in infinite detail. The constant also redefined what it meant for physical laws to be universal. Instead of smooth, scale-free equations, nature was governed by rules that changed character depending on scale. At large scales, Planck's constant fades into irrelevance, and classical certainty returns. At small scales, it dominates, reshaping behavior in ways that defy intuition. Reality became layered rather than uniform. Over time, Planck's constant proved to be more than a numerical value. It became a cornerstone of modern physics, appearing in equations that describe atoms, molecules, and fundamental particles. It set the scale at which quantum effects emerge and classical ideas fail. Without it, the structure of modern science would collapse. Technologically, this constant underlies much of the modern world. Electronics, medical imaging, communication systems, and emerging quantum technologies all rely on processes governed by Planck's constant. What once seemed like an abstract mathematical tool now shapes everyday life. The introduction of Planck's constant revealed that the universe operates with built-in limits. It showed that reality is not infinitely smooth, but structured at its deepest level. By defining what cannot be made smaller, more precise, or more continuous, it quietly changed humanity's understanding of what can be known and how nature truly works. The shift from a continuous to a discrete view of reality marked one of the most profound changes in human understanding of nature. For centuries, the universe was imagined as smooth and unbroken, governed by laws that allowed physical quantities to change in infinitely small steps. Motion flowed without interruption, energy spread seamlessly, and time advanced like an unbroken line. This picture felt natural because it matched everyday experience and aligned perfectly with classical physics. As experiments probed deeper into the microscopic world, this smooth image began to fracture. Phenomena at atomic and subatomic scales refused to behave in continuous ways. Energy did not increase or decrease gradually as expected. Instead, it appeared to jump between fixed values, occupying specific states and skipping everything in between. This behavior was not occasional or rare. It was consistent, repeatable, and universal. The realization that reality is discrete at its foundation challenged intuition. Discreteness implies limits, steps, and boundaries. It suggests that nature operates more like a digital system than an analog one, where certain values are allowed and others forbidden. Classical physics had no place for such restrictions. Its equations assumed infinite divisibility, where change could always be made smaller and smoother. Discrete behavior broke this assumption entirely. At the heart of this shift was the behavior of atoms. Atoms did not emit or absorb energy continuously. They transitioned between specific energy levels, producing sharp spectral lines rather than continuous bands of color. This observation could not be explained unless energy itself was quantized. The same pattern appeared in electrons, vibrations of atoms, and interactions between light and matter. Reality, it seemed, was built on allowed states rather than endless possibilities. This new understanding altered the meaning of stability. In a continuous world, systems could occupy any energy value, and instability was often expected. In a discrete world, stability emerges naturally. Systems remain in fixed states until a precise amount of energy forces a transition. This explained why atoms do not collapse and why matter has consistent structure. Discreteness brought order where continuity predicted chaos. The shift also introduced probability into the description of nature. If systems can only occupy certain states, transitions between them cannot always be predicted with certainty. Instead of smooth trajectories, physics began to describe likelihoods and distributions. This did not mean reality was random, but that it followed rules different from classical determinism. Outcomes were constrained, but not always predictable. Accepting a discrete foundation required abandoning deeply held assumptions. Continuity had been associated with realism and clarity, while discreteness felt artificial and abstract. Yet evidence repeatedly favored the discrete view. The universe, at its smallest scales, did not care about human preference or intuition. It revealed its structure through consistent experimental results. The transition from continuous to discrete reality did not eliminate classical physics. Instead, it redefined its role. Classical laws remained valid where discrete steps were too small to observe, creating the illusion of smoothness. This layered understanding allowed both views to coexist, each accurate within its own domain. Beyond physics, this shift influenced philosophy and technology. It changed how humans thought about knowledge, certainty, and the limits of understanding. It also enabled technologies based on controlled energy states, from digital electronics to quantum systems. The realization that reality is discrete rather than continuous was not loud or sudden. It emerged quietly from experiments that refused to fit old theories. Yet its impact was revolutionary. It replaced the idea of an endlessly smooth universe with one built on structure, limits, and precision, reshaping how humanity understands the fabric of existence. The fact that Max Planck himself resisted the full implications of his own discovery reveals how deeply revolutionary the idea truly was. Planck was not a scientist seeking to overthrow established thought. He was a careful, conservative physicist who believed strongly in the completeness and reliability of classical physics. His mindset reflected the dominant scientific culture of his time, which valued continuity, determinism, and order. The idea that nature might behave in fundamentally discontinuous ways conflicted with his deepest convictions. When Planck introduced the concept of energy quanta, he did so out of necessity rather than belief. He was attempting to solve the Blackbody radiation problem using any method that worked, even if it felt unnatural. For Planck, the assumption that energy could only be exchanged in discrete amounts was a mathematical device, a formal trick that allowed the equations to match experimental data. He did not initially see it as a literal description of physical reality. This reluctance is crucial to understanding the historical moment. Planck did not celebrate his result or proclaim a new worldview. Instead, he hoped that a deeper classical explanation would eventually replace his assumption. He believed that quantization was temporary, a sign of incomplete understanding rather than a permanent feature of nature. This cautious attitude highlights how radical the idea truly was, even to its creator. Planck's resistance also reflects the emotional cost of scientific revolution. Accepting quantization meant abandoning the belief that nature could be fully described by smooth, deterministic laws. It meant accepting limits on knowledge and continuity, concepts that had defined physics for centuries. For Planck, this was not merely a technical shift, but a philosophical rupture. The turning point came when other scientists extended his idea beyond Blackbody radiation. Albert Einstein applied energy quanta to light itself, explaining the photoelectric effect. This interpretation suggested that light behaves as if it consists of particles carrying fixed energy amounts. Unlike Planck, Einstein took the idea seriously as a statement about reality. This forced the scientific community, including Planck, to confront the possibility that quantization was not a mathematical convenience but a fundamental truth. Even then, Planck remained cautious. He accepted the usefulness of the idea, but remained uncomfortable with its implications. This hesitation underscores the strength of classical intuition and the difficulty of abandoning deeply ingrained beliefs. Scientific progress, in this sense, was not driven by immediate acceptance, but by persistent evidence that left no alternative. Over time, the success of quantum ideas became overwhelming. Atomic spectra, chemical behavior, and the stability of matter all depended on quantized energy levels. Each confirmation narrowed the space for classical interpretation. Gradually, Planck acknowledged that his discovery had uncovered something essential about nature, even if it contradicted his original expectations. Planck's reluctance serves as a powerful reminder that scientific revolutions often begin unwillingly. Transformative ideas do not always arise from bold visionaries seeking change. Sometimes they emerge from careful thinkers confronting facts they cannot deny. The strength of science lies not in comfort, but in its capacity to accept uncomfortable truths. In the end, Planck's resistance did not diminish his contribution. Instead, it emphasized its significance. The fact that such a cautious scientist introduced an idea he himself struggled to accept demonstrates how compelling the evidence was. His journey from skepticism to reluctant acceptance mirrors the broader transformation of physics itself, moving from classical certainty toward a deeper, more complex understanding of reality. The final and perhaps most far-reaching aspect of Max Planck's work is how it reshaped modern science and technology, transforming both understanding and application in ways that were unimaginable at the time. The introduction of energy quanta, the recognition of Planck's constant, and the move from continuous to discrete models did more than resolve theoretical puzzles. They opened an entirely new frontier in physics, one that would ripple through generations of scientific thought and practical innovation. Before Planck, physics had largely been a descriptive science. Classical laws explained motion, light, heat, and electricity with remarkable accuracy at macroscopic scales. Engineers could build machines, predict planetary motion, and harness energy with confidence. Yet these accomplishments were bounded by the assumption that nature was continuous, predictable, and deterministic. The small-scale behavior of atoms and radiation, largely invisible at everyday scales, remained a theoretical blind spot. Planck's work illuminated that blind spot and, in doing so, revealed that the microscopic universe operates according to different rules than the familiar macroscopic one. The implications of his discovery extended immediately into the field of quantum mechanics. Planck's quantization laid the groundwork for the models of atomic structure developed by Niels Bohr, who explained the stability of electrons in atoms using discrete energy levels. These models, in turn, led to a deeper understanding of chemical bonding, spectroscopy, and the behavior of matter under extreme conditions. Without Planck's initial insight, much of modern chemistry and material science would lack the theoretical foundation upon which they are built. Technology, too, owes much to Planck's revelations. The realization that energy is quantized led directly to innovations in electronics, semiconductors, and lasers. Lasers, for example, rely on atoms transitioning between discrete energy levels to produce coherent light. Transistors, the building blocks of modern computers, operate on principles that reflect quantum behavior in solid-state materials. Medical technologies, from MRI machines to PET scans, harness quantum phenomena rooted in Planck's initial discovery. Even everyday devices like smartphones and LED depend on understanding energy quanta and their interactions with matter. Beyond specific applications, Planck's work transformed the very approach scientists take to understanding nature. It demonstrated that assumptions, no matter how long, standing or intuitive, must always yield to evidence. Classical physics had been successful, elegant, and deeply trusted, yet it was incomplete. Planck's contribution highlighted the importance of questioning foundational principles and being willing to embrace radically new concepts when the data demanded it. In this sense, his work exemplifies the intellectual humility that is at the heart of scientific progress. Planck's ideas also changed the philosophical framework of science. Determinism, once assumed to govern every aspect of the universe, was no longer absolute. Probability and uncertainty became essential features of physical theory. Nature was revealed to be granular, structured, and constrained by rules invisible to classical intuition. Scientists learned that predictability exists within limits, and that at fundamental scales, phenomena must be described using new, sometimes counterintuitive principles. This shift influenced not only physics, but also philosophy of science, epistemology, and even the broader world view of humanity. Furthermore, Planck's work inspired a generation of physicists to explore the unknown with courage. Einstein, Schrödinger, Heisenberg, and countless others built on the foundations he laid, developing quantum theory, quantum field theory, and ultimately, the standard model of particle physics. Each of these advances would have been unimaginable without the first recognition that energy is quantized. Planck's discovery became a cornerstone, supporting an entire edifice of modern scientific achievement. The impact of Planck's work also demonstrates how small, subtle insights can have transformative consequences. His initial proposal appeared modest, a technical fix to a specific problem in blackbody radiation. Yet its implications radiated outward, touching every branch of physical science and technology. This underscores the power of careful observation, deep reasoning, and willingness to follow where the evidence leads, even when it challenges deeply held beliefs. In the modern world, Planck's influence is everywhere. From quantum computing to medical imaging, from lasers to solar cells, the principles he uncovered guide both practical innovation and theoretical exploration. His work reminds us that progress is often incremental at first, but can eventually revolutionize our understanding and capabilities. Through his careful, measured steps, Max Planck quietly redefined reality, leaving a legacy that continues to shape science and technology more than a century later.